Good morning, everyone. I hope that you guys are having a good start to your Thursday here. Um, I have to make two announcements, and that is I got some emails on Tuesday that I haven't resolved. I will take care of those today. Likewise, emails that I received yesterday, I will take care of those today. So, in the event that you're waiting for a response, I apologize for the delay, um, but I will take care of that today. Now, where we are in this class is we're nearly done with chapter 6. Now, this particular section that we're going to be working through, these sections 6.5 and 6.6, are all about gases. And it's my opinion that gases, I think, are a little bit tangible and I guess relatable. Like there are things that we'll talk about with respect to gases that you've maybe observed. For instance, if you put let's say you got a Ziploc bag and you inflated it as much as you could, and then you put it in the microwave for 15 seconds or something like that. Chances are that Ziploc bag that's inflated to capacity is going to erupt. It's going to burst. And that's because the volume of the bag can no longer contain all the space that all of the gas molecules need between them. And so that's something that you've maybe never put it in the terms of, well, I've increased the heat, therefore the pressure has increased, therefore the volume must increase. But that's what we're going to be doing today. We're going to be putting gases kind of in the terms of, well, or looking at relationships of gases in kind of scientific terms. So the kinetic theory of gas is something that can be displayed with this video. Just a second. Where we have all of these gas molecules and gas particles moving randomly in a container. The collisions of these are between the particles and the walls. They are considered to be basically a relationship to the pressure that the gas is experiencing. So the increase in number of collisions is going to also lead to an increase in the pressure felt by the system. Now, what you should notice about those is that they're simply bumping and they're hitting one another and they're not losing any energy in the process. There we go. Now, there is a relationship between all things temperature, volume, and pressure and amount of a gas. So these are the four things that anytime that you are thinking about a gas, you need to be thoughtful of, well, what's the temperature? What is the pressure that is either the pressure felt by the gas or the pressure that the gas is exerting? How much of that gas is in that container? And then what is the overall volume of that container? Now, with this simulation, what we can do is we can kind of tinker around with our gas laws. So here what we can do is, what we're going to do is put a certain amount of a gas into a container. Now, the what we can do in this process as well is we can hold a certain number of different variables constant. For instance, we can see what happens when we increase the pressure of our gas. We can see what happens when we increase the temperature of our gas. So when we heat up this system, we're going to see those gas particles slowly but surely begin to move a little bit faster. Those collisions are going to increase in frequency as we increase the temperature. Now, if we take the volume of this system and we cut it in half, well, what happens to the number of collisions between the particles and the particles in the wall? Well, if we cut down the volume, then those particles have less space within which to work. If we we increase our pressure, which, we decrease our pressure, we let the system grow in volume, well, then what's going to happen is those gas particles are going to slow down. So there's a relationship between all these different variables in terms of the number of collisions that are taking place. And that's one of the important things to understand about um, gases and to think about them as individual particles. Now, what we haven't really gotten into very much is, or we've talked about this a little bit, but if we look at this number right here, 6.02 times 10 to the 23rd particles, that's our base unit for number of particles in 1 mole. So if you have a mole of anything, you have a mole of particles, of gas particles, or gas molecules, you have 6.02 times 10 to the 23rd particles. Our base pressure is going to be measured in atmospheres. Sometimes it's measured in kilopascals. Now, a temperature, we always, for gases, think about temperature in terms of Kelvin. So I will give you a temperature in degrees Celsius, but you need to remember to add 273 to it to determine the temperature in Kelvin. Last but not least is volume. Well, 1 liter is equal to 1,000 milliliters. That's one of the conversions that we talked about earlier on in the semester. Now, pressure or gas laws breaks down into a couple of different relationships: pressure and volume and temperature, pressure and temperature, and volume and amount. So what this means is whenever we're looking at some of these variables, that means we're holding the other ones constant. So whenever we are talking about a relationship between pressure and volume, what we are holding constant is temperature. So one way to think about this is what's going to happen to a container, or what's going to happen to the pressure if if we increase the volume and the temperature is held constant. So a way to think about this is we've got a container, gas particles in there. And let's say the pressure is equal to, I'm just going to give it an arbitrary unit of 1. I'll say 1 atmosphere. Now, what do you think is going to happen to this pressure if our volume is increased? So the volume of this container, the volume that this container holds, increases. What do you think all these particles are going to experience? Are they going to experience more pressure, or are they going to experience less pressure? And pressure is a force applied over an area. So the question is basically, do these gas particles have more or less space in which to work? They've got a lot more space, in which case their pressure that they're experiencing will decrease because the volume increased. Now, if you look at this kind of visual here what we have is marshmallows in a vacuum chamber, and we're going to decrease the pressure. So what's going to happen to those marshmallows is they're gradually going to expand. They're going to grow. As soon as that pressure is relieved, however, what's going to happen? Or that pressure is released and that pressure increases, well, then they're going to contract. They're going to get smaller and smaller. So these are held at a certain temperature, maintained at a constant temperature. And this is what is known as Boyle's law. If you decrease the pressure, well, then the volume is going to increase. And vice versa. If you increase the pressure, so increase pressure, then what's going to happen is your volume will decrease. Decrease. So this is our relationship here, pressure and volume. What we have is, this is a good example of, it's kind of a relationship, and or it's kind of a good way to understand how a car works, an internal combustion engine. So most vehicles that are out on the roads, except for electric vehicles, have an internal combustion engine. And so what happens is there's a little bit of a gas down here that's ignited, and that it explodes and expands, and that's going to force this chamber or this piston in a car to go up. Um, so, and that's because the gas expands and it forces that pressure to decrease. So the relationship, the way to quantify this is to say P1 V1 is equal to P2 V2. Another way to think about this one right here is initial. And then to think about these twos as your final. So if you have a gas in a container and the initial volume is, let's say it's 3 liters, and the pressure is 1 liter. We're going to put these numbers in. So our pressure is 1 atmosphere. Our volume is 3 liters. Then our pressure so our pressure decreases to 2 atmospheres, or I'm sorry, it increases to 2 atmospheres. In order for these two values to be equal, what does V2 have to be? It's got to be 1.5 liters. So it has to be cut in half. So what happens to the volume when we double the pressure at constant temperature? It's halved. So when you see a question like this, what happens to the volume when we double the pressure? This is an example where I am always, if I'm solving this problem, I'm almost always going to punch numbers in. So I'm going to say, okay, initially I'm not given any numbers for this, but what happens to the volume when we double the pressure? Okay, we doubled the pressure. So I'm just going to say my pressure went from 1 to 2. Okay, now my volume. Well, volume is, let's just come up with an arbitrary initial volume, which is what we did. We came up with 3 liters. So then after the fact, what's my volume? It's 1.5 liters. So I'm always going to plug numbers in there so that it's easier for me to swallow, to like process, to swallow. It's an easier pill to swallow. It's easier for me to understand and do that calculation. This is the sort of calculation that there are some people who they are fantastic with mathematical relationships, and they don't even have to plug the numbers in. They just understand them. And I am not one of those people. So I'm going to plug numbers in. P1V1 equals P2V2. That's the relationship with pressure and volume when the temperature is constant. This right here is a huge part of this because if the temperature increase or decrease, that's one variable, which if we go all the way back here, we have four variables that we have to consider. So really, when we look at this question, the temperature is held constant and the amount of the gas is held constant. So those are two things that you need to kind of be thoughtful of when you're doing this sort of calculation. Next up, volume and temperature. So, okay, let's go ahead and do a little bit of a summary here. Pressure and volume is Boyle's law. That's pressure and volume. The relationship between pressure and volume when temperature is held constant is Boyle's law. Meanwhile, is old Chucky Charles's law that gives us a relationship between volume and temperature. Volume is equal to constant times T. Okay, so what do you think will happen to the volume when we increase temperature at constant pressure? Okay, so this goes back to our, we've got our bag of, or our Ziploc, and we throw it in the microwave. The pressure inside the microwave is not going to change, but the temperature inside the microwave is going to change. The temperature of the gas inside our Ziploc bag is going to change. Now, if we're seeing those increase, then what happens to our volume? Well, that the gas in the Ziploc bag is going to expand. And at some point, that Ziploc bag, it's a Ziploc, so it has some, it's a plastic, so it has some kind of, what's the word that I'm looking for? Some ability to expand and contract. But at some point, you'll exceed that. And then what's going to happen is, well, that bag's going to burst because the gas that was contained in that bag needed a higher volume. So, what will happen to the volume if we increase the temperature? Well, the volume will increase as well. Any time that you've ever heated a closed container, which what are you always told about heating closed containers? Never do it. If you've ever made soup in a microwave or something and you put it in like a Tupperware thing and closed it and threw it in the microwave, what's going to happen is, well, it's going to pop. It's going to expand until the volume that is in there is not enough. So now, when we have this relationship where both volume and temperature, if volume goes up, so too does temperature. If temperature goes up, so too does volume. Then we have a relationship where volume is over temperature. So what we have to do, though, is we have to use a temperature that's in units Kelvin. Now, what we're seeing over here on the right-hand side is just the balloon that was inflated at room temperature. And then someone got liquid nitrogen, which if you've ever seen the movie Terminator 2, liquid nitrogen was what helped kill the T-1000. If you've never seen Terminator 2, then I think you should see Terminator 2 because it's a really great movie. But this liquid nitrogen, what that causes is, well, first of all, liquid nitrogen is extremely cold. That's what's used to cool. I mean, it's used to cool supercomputers sometimes. It's used to cool any number of things because of how cold it is. Um, what we see is this balloon and this liquid nitrogen, which I think that liquid nitrogen is like around negative 40 degrees Celsius. Um, that is going to cause this balloon to basically shrink, and the gas inside it to shrink super fast. And provided that the liquid nitrogen doesn't break the balloon or the balloon doesn't break under all the stress, once that balloon warms back up, what's going to happen to the volume? That's going to go up as well. So the relationship between volume and temperature is that When one goes up, the other goes up. This is a direct relationship. So this is a direct relationship, meaning that this is an inverse relationship because one goes up, the other goes down. So, all right. So we've got Boyle's law. And this is an inverse. We've got Charles's law. This is a direct relationship. And now we're on to what's the relationship between pressure and temperature. This is the Gay-Lussac law or Gay-Lussac's law. And this asks us, what do you think will happen to the pressure when we increase the temperature at constant volume? Okay. So let's again use that example of the Ziploc bag. But now let's say that that Ziploc is indestructible. So this is an indestructible Ziploc bag. You increase the temperature, but the volume of that Ziploc remains constant. Now, we were just talking about when we were looking at Charles's law, imagining that, well, the volume is going to have to expand. And then when it reaches its kind of stopping point, the bag bursts because there's so much force and pressure that's put on that bag. Here, what we have is a situation where the volume can't expand. The volume is a constant. So Gay-Lussac's law says that if the volume is held constant, when the temperature goes up, what's the pressure going to do? It too will increase. So notice the relationship here. Pressure over temperature, much like volume over temperature, unlike pressure times volume. So when you're dividing these things, dividing these variables, that is a hallmark of a direct relationship. When pressure goes up, temperature goes up. When pressure goes down, temperature goes down. When temperature goes down, pressure goes down. The important thing about these calculations is, however, that the units must be in Kelvin. Now, our last relationship is the one that we kind of haven't really dug into that much. And that is volume, or sorry, that is amount. So when we have a relationship between volume and amount, okay, so this is Avogadro's, and actually let's go back and rehash these. We've got Boyle's. This is inverse. We've got Charles's. And that's a direct relationship. And then we have Gay-Lussac's, which is also direct. So another way that you can look at all of this is I can ask you a question like A times B equals C times D. And I could ask you, what's the relationship between A and B? Well, I want you to know that because A times B, so when we're looking at the product of two things, that's inverse. Whereas if I said, okay, A over B, this would be direct. So when you see these math relationships and you see these equations, I think it's important to think about that and to be able to identify them just based on the structure of the equation. Now, what do you think will happen to the volume when we increase the amount of gas particles at constant pressure? This is Avogadro's principle. So Amadeo Avogadro was a scientist who ultimately came up with the concept of a mole. Now, this one I think is like the most intuitive. What do you think will happen to the volume when we increase the amount of a gas? Okay, so let's say that, I've mentioned Ziploc bags several times, and I'm going to do it again because what's on my desk? A handful of Ziploc bags with photographs in them. Okay, so here is a Ziploc bag. My question for you is there any gas in here? Yeah, there is. No doubt about it. Okay. Now, is there more gas in here? There is. How has the volume of this gas changed? Has it increased or has it decreased? Effectively, that's what this question is asking. What do you think will happen to the volume when we decrease the amount of gas particles at constant pressure? So here's our starting point, and here's our end point. The amount of gas decreased, and the volume of that gas also decreased. Okay, so before we proceed, V went down and amount, or N, which here, let's jog back for a second. Amount gets the single or the single letter N to indicate this. Okay, so volume decreases. What happens to N? It also decreases. So there's our relationship. Now, what happens to the volume when we double the amount of gas at constant pressure? Okay, so here what we're going to do is we're going to say, well, V1, I'm just going to plug 1 in for that, is equal or over 2 is equal to V2, which is what we don't know, over, and now we're doubling the amount of gas, so we're going to jump that up to 4. So what's going to happen to my volume? For 1/2 to be equal to something over 4, it has to double. So that's really pretty much the high points of all of our relationships. Now to go back here and fill in our last one, we've got Avogadro's law. And this is also a direct relationship. So I'll ask you questions about the individual relationships, all these laws. I'm expecting you to be able to identify the laws. If I give you an equation like this right here, I'd expect you to say, oh, well, that's Gay-Lussac's law. Also, if I say the direct relationship between pressure and temperature is described best by the Gay-Lussac law, I expect you to know those sorts of things. But this is really the nuts and bolts of chapter 6.5 and 6.6. You've got a quiz that goes up today, and then there will be, yeah, it goes up today. Like I said, I'm going to address some of the emails that I received Tuesday, and then I got one yesterday. I'm going to take care of those. But if nobody has any questions, I'm going to go ahead and stop my recording.